So we'll be starting with this topic, which is estimators today, which is the sixth topic in the second unit under the statistical and econometrical methods series. And here is the flow through which we'll be studying the topic. Few key terms which we'll be seeing a lot in the chapter. So to start with, what are estimators? Or I can say it rather, what is an estimator? See, in sampling, we already studied that whenever we want to study a huge population, we take a sample out of it and we work out certain parameters like population mean, the variance, the other things, so as to know the characteristic of that certain population which we want to study. Now, this estimator is the rule, or we can say a function, that provides an estimate of that population parameter based on that sample data. It actually tells you about the unknown. It is used to make inferences about these parameters only using information from the sample. So we can say that process of guessing, when we are guessing, it's called estimation, and what we guess is called the estimator. And that is why it is typically denoted as a function of that sample data. I have taken a very simple example to explain. For example, if we want to estimate the average height of all students in certain university, what we can do, we can use the mean height of a sample of student that we have taken out of that entire population of the university, and we can use it as an estimator of that population mean. So the estimator itself is a random variable. Why? Because it is a function of the random sample data that we have to collect it. And so its value varies from sample to sample because of this randomness that has been inherent in the sampling process. And we can denote it like, for example, if the population mean is mu, then the sample mean can be capital X bar. So it is the estimator of that population mean. Similarly, if the population variance is sigma square, then the sample variance, which is the estimator of this population variance, can be taken as S square. So that is how we'll be presenting it or denoting it. Let's do some math. So here we have taken a very, very simple equation to explain the relationship. See, mathematically an estimator can be represented, as you can see here, as a function, as I already told you earlier, theta cap, which is equal to g, small g under bracket, capital X1, X2 and further on till Xn, where this theta cap is the estimator of any population parameter theta. X1, X2, Xn are the sample observations that we have taken, and g is some function that calculates the estimator based on that sample data that we have taken out of the population. Now, how to know that the estimator is working correctly? So there are certain properties to judge it and find it. So first of all, the estimator should be totally unbiased, which means that an estimator is said to be unbiased. It will be called as an unbiased estimator if its expected value is equal to the true value of the parameter being estimated that it is representing. Or we can say on average it hits the target parameter. So an estimator that systematically overestimate or underestimate the parameter will be considered as biased. Secondly, it should be consistent, which means that it should be the one where the estimates become closer to the true parameter value as the sample size increases. It should not change. So this consistency ensures that by collecting more data, we can improve even the accuracy of our estimate. Then the property says that it should be efficient. Efficiency refers to the variance here. Among all unbiased estimators, an efficient estimator will have the smallest variance. An efficient estimator provides more precision and is less spread out around the true parameter value. So therefore, it will be lesser and lesser spreading out, and so the variance value would be smaller. Further, it should be sufficient. What sufficiency means? That a sufficient estimator captures all the information in the sample that is needed to estimate the parameter, especially the important one. No other statistic calculated from the same sample can provide any additional information about the parameter, or it will be called the insufficient estimation. Now this concept is the sampling distribution of our estimator. See, this sampling distribution is nothing else but the probability distribution of our estimator when we are taking out the repeated samples from the same population. Meaning to say that it explains how the estimator would behave over all possible samples drawn down from the same population. So now what are the key points of this sampling distribution? So first of all, the mean of the estimator. It says that the expected value of the estimator is called the bias. An estimator is said to be unbiased if the expected value is equal to the true population parameter. That we have studied already in one of the properties of a good estimator. The second key point talks about the variance of the estimator, meaning to say that the variability or spread of the estimator is measured by its variance. So a good estimator will have a small variance. We have already studied that, meaning that even if we take repeated sample from the same population, it should be true or close to the true population parameter, should stay the same. And the further key points say that the standard error, which is the standard deviation, error tells about the standard deviation of the estimator's sampling distribution, and it should be lesser and lesser. The more there will be errors or the standard errors, the more will be there the more it will be the discrepancy in the estimation or the results from the true parameters. So what are the factors that affect this sampling distribution? So first of all, the size of the sample would really matter, because larger sample size generally lead to more precise estimators. And second of all, the nature of the population that we are studying, it's also very, very important, whether it's normal or not, or little unique by nature. So both of these factors will affect definitely the sampling distribution. Further, there is just a quick reminder of the things that we have already studied, like the estimator, what is the sampling distribution, what is called an unbiased estimator, variance, standard error, etc., that you can just quickly go through. So in the conclusion, we can only say that the concept of estimator and its sampling or the probability distribution is fundamental for understanding how we make these statistical inferences and how we assess the reliability of the estimates that we have obtained from certain sample data that we have collected from a population. Thanks.